Here I will be solving another example on propped cantilever beams using consistent deformation method. Here I will be considering different flexural rigidity for different parts of the beam. Let us see how to solve this. So the question is given as analyze the propped cantilever beam using consistent deformation method. I will say CDM and draw shear force diagram, bending moment diagram and elastic curve. This is the question given, and the propped cantilever beam is given like this. There is a partial UDL of 30 kilonewton per meter over a span of 3 meters, and there is a point load of 50 kilonewtons over a span of at a distance of 2 meters from the prop. So let us take these points as point A, point B and point C. Now here in this question, let us consider the flexural rigidity of AB is given as 2I and flexural rigidity of BC is given as 1I. So how do we consider this? So here, as usual, we know the consistent deformation equation is given as deflection due to loads plus deflection due to prop is equal to total settlement of supports, and deflection can be calculated as area of bending moment diagram divided by EI multiplied by centroidal distance. So here we will be splitting this beam into two cantilever beams, in fact 3 cantilever beams. One is with UDL, that is partial UDL. This is 3 meters. This is 30 kilonewton per meter. This is point A, point B and point C. And the flexural rigidity for AB is 2I, and for BC it is 2 meters and flexural rigidity is I. This is one cantilever. The other cantilever is cantilever with point load of 50 kilonewtons. This is 3 meters and 2I, and this is 2 meters and I. It's point A, point B, point C. And the other cantilever will be cantilever with prop. This is point A, point B, point C. And here this is 3 meters, 2I. This is 2 meters and I. So let us consider this prop as RC, that is reaction at point C. So these are the 3 beams which have been divided based on loads and based on props. Now we have to draw the bending moment diagrams for each of these cases. So for cantilever with partial UDL, it will be a hogging bending moment like this, and this will be negative, and the value here will be 30 into 3 into 3 by 2, which is 135 kilonewton meter. And this is point A, point B and point C. And for cantilever with point load, we will again get a hogging BMD, which will be triangular variation like this. And the bending moment here will be 50 into 3, that is 150 kilonewton meter, which will be hogging. This is point A, point B, and point C. And for cantilever with prop, we will get sagging bending moment. So the BMD will be positive, and the bending moment at point A will be 3 plus 2, that is 5 times RC. This is 5 RC. This is point A, this is point B, this is point C. Now here what we have to notice, this entire region is 3 meters 2I, this is 2 meters and I, this is 3 meters and 2I, this will be 2 meters and I, and here we will have to divide this into smaller parts because we have varying flexural rigidity. So A to B, this will be 3 meters and 2I, and B to C will be 2 meters and I. So at this point B, the moment will be 2 times RC. So this will be 2 times RC. Now we know this is 5 times RC. So we know this height is 2 times RC. So the remaining height will be 5 minus 2, that is 3 times RC. So this is about the bending moment diagrams. Now the centroidal distances have to be considered from the centroid till the prop for each BMD. And here, because we have divided this into different shapes, we have to consider central distances respectively. This will be X bar for the triangular portion. This will be X bar for rectangular portion. And this will be X bar for the small triangular portion. So this has to be remembered. Now we have the bending moment diagrams and the centroidal distances, so we can apply our consistent deformation equation. So for the first BMD, the area will be, it is hogging BMD, so it will be minus 1/3 base into height divided by, this is 2 EI, so this will become 2 EI, and the centroidal distance will be from this point till point B, it is 3/4 of the base, and the remaining is 2 meters. So this will be 3/4 of 3 meters plus 2 meters. Next, for this triangle, it is negative, so it is minus. The area is half into base into height divided by, this is again A to B is 2I, so it will be divided by 2 EI, and the central distance for the triangular portion, it will be 2/3 of base, and the remaining is 2 meters. So this will be 2/3 of 3 meters plus 2. And here we have three geometric shapes. We will first consider the bigger triangle. So the entire BMD is positive, so it will be plus. Yeah, for the bigger triangle, the area is half into base 3 meters. Height of this triangle is 3 times RC divided by, and EI for this triangle is 2I, so this will be 2EI, and the centroidal distance is, for the triangle it will be 2/3 of base plus the remaining 2 meters, so it will be 2/3 of 3 plus 2. This is for the bigger triangle. Next we will consider the rectangular portion, so this will be plus, area of rectangle is 3 meters into height of the rectangle is 2RC divided by, and it lies in 2EI region, so divided by 2EI, and the centroidal distance will be half of 3 meters plus 2, so this will be half of 3 plus 2, plus the smaller triangle lies in 1 EI region, so the area is half into base into height of this triangle is 2 times RC, so 2RC, but this will be divided with 1 EI, so it is simply divided by EI, and the centroidal distance for the small triangle is 2/3 of 2, 2/3 of 2. Okay, this is equated to total settlement of the supports. So here this total settlement of supports is not mentioned in the problem, so you can take it as 0. So this will be the consistent deformation equation applied for each BMD. Now if we simplify this, we can calculate the unknown value of RC, because the only unknown here is RC. So upon simplification, you will get this as minus 286.875 minus 450 plus 9 times RC plus 10.5 times RC plus 2.67 times RC is equal to 0. Now if I solve this equation, I will get the value of RC as 33.24 kilonewtons. So this is the reaction at C. So we have the propped cantilever like this with partial UDL and a point load. The UDL is 30 kilonewton per meter. The point load is 50 kilonewtons. This span is 3 meters and this is 2 meters. This is point A, point B, and point C. So now here we have calculated the value of RC as 33.24 kilonewtons. And because we have a fixed support at A, we will have a vertical reaction at A. Let us consider it as RA, and it can be calculated by considering sum of all vertical forces is equal to 0. So that will give us RA plus 33.24 is equal to 30 into 3 for the UDL plus 50 kilonewtons for the point load. So here I'm equating upward forces is equal to downward forces, and from this equation I can find RA which will be 106.76 kilonewton. So now I have determined the value of reaction at A, which is 106.76 kilonewton. So I know both the reactions. I can draw the shear force diagram. So I will draw the shear force diagram in kilonewtons. The sign convention is left to right. Upward forces are positive and downward forces are negative, right? So at A, there is an upward force 106.76. From A to B, there is a UDL acting downwards 30 into 3. So 106.76 minus 30 into 3, I will get 16.76. And at B, there is a 50 kilonewton downward. So it will be 16.76 minus 50. That will be minus 33.24. And from B to C, there is no load. So it will be uniform. And at C, there is a point load acting upwards. So it will be plus 33.24. So minus 32.24 plus 32.24, you will get 0. Above the reference is positive, below the reference is negative. So this is a shear force diagram. And to draw the bending moment diagram, we have to calculate bending moments at various points. Calculation of bending moments at various points. And here the sign convention which we will use is sagging bending moments are positive. So we know at prop the bending moment will be 0. So bending moment at point C is 0. At point B, if I consider right hand side, there is 33.24 into 2, which is sagging. So it will be 33.24 into 2, that is 66.48 kilonewton meter. And bending moment at A, if I consider right hand side, will be 33.24 into 5 meters, which is sagging. So it will be 33.24 into 5, 50 into 3. This will be hogging. So it is minus 50 into 3. And due to UDL, it will be 30 into 3 into 3 by 2, which will also be hogging. So it is minus 30 into 3 into 3 by 2. So this is equal to minus 118.8 kilonewton meter. So these are the bending moments at various points. Now you can draw bending moment diagram in kilonewton meters. So this is your reference. At point C, it is 0. At point B, it is positive 66.48. And at point A, it is minus 118. So it will be in the negative region, 118.8. So this will be a straight line here. And from A to B, you have a UDL. So this will be a parabola, curved portion. And from B to C, there is no load. So this will be a straight line, right? So this is a curve and this will be a straight line. And if you want to calculate the point of contraflexure, you can consider a section here at a distance x from point C. You can write bending moment at section x and you can write d by dx of bending moment at x is equal to 0. This will give you the location of point of contraflexure. So that can be done if asked in the question. So this is about the bending moment diagram and the elastic curve. You can draw the given beam without the forces. So here in BMD, the downward portion is hogging, the upward side is sagging. So from point A to this point, your beam has to hog like this, and from point of contraflexure till point C, the beam is sagging. So this is your point of contraflexure, and this is the elastic curve. So these are some of the examples on propped cantilever beams using consistent deformation. In my next video, I'll be explaining how to solve fixed beams using consistent deformation method. So keep following.